Welcome to this video. We shall understand the concept of Nernst equilibrium potential in the next couple of minutes. In a hypothetical situation, a solution containing a cation, X, at a concentration of 1 molar is present, on side A, of a semi-permeable membrane. On the other side, B, we have the same cation present, but with concentration of 0.1 molar. So now, cation, X, shall move from side A to side B, down the concentration gradient. If we want to prevent this downhill diffusion, what can we do? Well, we can use a negative charge or an electric current of a particular voltage, on side A, so that no excess cation, X, can diffuse from side A to side B. If we employ voltage of such a strength that exactly balances the excess positive charge, on side A, then we can achieve this. Let that current voltage used be minus 60 millivolts. Now, let's go a step ahead. We have just determined that if we use a voltage of minus 60 millivolts, on side A, we can prevent diffusion of excess cation, X, from side A to side B. But, what happens if we use a voltage which is slightly more negative than minus 60 millivolts? Consider that we use a voltage of minus 70 millivolts, on side A. Obviously here we have more negative charge present than what is required to balance the excess cations. So due to this newer condition of excess negative charge, cation, X, will now start moving from side B to side A. Note that, till now, we have used a negative voltage on side A, but we can also prevent diffusion of cation X, in the first case, from side A to side B, by using a positive voltage on side B. This is because positive charge on side B will repel the excess cations that tend to move from side A to B. So summarizing, we learnt that 1. We can stop ionic diffusion despite of its concentration gradient across a membrane by using an electric current of a particular voltage on one side of the membrane. 2. If we increase the strength of voltage on the same side, we can also cause the ionic movement against the concentration gradient. Basically, ions move under the effect of two forces. One is the chemical potential generated by its concentration gradient. Second is the electrical potential, which can be generated by using an electric current as we just did. The voltage which is used to prevent ionic diffusion or even to cause movement against or towards the concentration gradient is known as electrical potential. Whereas, the concentration difference on either side that causes downhill diffusion is called as chemical potential. Together, it is known as electrochemical potential acting on the ion. And the net flow of a particular ion will be, from where its electrochemical potential is higher to where its electrochemical potential is lower. In mathematical terms, using experimental setup, we can calculate the relationship between electrical potential and the chemical potential affecting a particular ion. This is given by the following equation. The absolute temperature, gas constant, Faraday's constant and natural logarithm all can be calculated, and then, the equation in its simpler form would be Here, we need only the concentration of the ion on either side of the membrane to arrive at the final value of electrical potential. So, Using this, we can compute the electrical potential difference between two sides of a semipermeable membrane that is equal and opposite to the concentration force that tends to move the ion from side A to side B. However, it is to be noted that Nernst equation provides the voltage that must exist on side A at equilibrium or to prevent diffusion. This is because concentration of ion X on side A was taken in the numerator, whereas that on side B in the denominator. If we simply invert the numerator and denominator, then we also need to change the negative sign in the main equation. Also to be noted is the charge Z for the concerned ion, which must be substituted in the equation. It will be positive value for a cation and negative value for an anion. Remember that the Nernst equation holds only for ions at equilibrium between two sides of a membrane, meaning that there should be no net flow across the membrane, or that the chemical potential causing it to diffuse downhill is exactly balanced by oppositely directed electrical potential preventing its downhill diffusion. In our earlier example, if we put the values for concentrations of A and B, and charge as +1, calculating for log gives us the value of -60 mV. This means that we require a voltage of about 60 mV to exactly balance a 10-fold concentration difference of a univalent ion. Let's look at another example. In this setup, an anion is present with the given concentration across two sides of a membrane. If we want to calculate the Nernst potential that is required to keep this anion in equilibrium across the membrane, then we substitute the values in the equation and we calculate for log to the base 10 for 2.2 divided by 1.2. The final value would be plus 15.79 mV. This is the amount of voltage that we require on side A to prevent diffusion of anion X. So summarizing, 1. If the measured electric potential difference across the membrane is equal to that calculated from the Nernst equation for a particular ion, then that particular ion is in electrochemical equilibrium across the membrane and there will be no net flow of that ion across the membrane. 2. If the measured electric potential difference across the membrane is of same sign to the electric potential calculated from the Nernst equation for a particular ion, but numerically less than the latter, then the concentration force is larger than the electrical force. So, net movement of that ion occurs in the direction of concentration force. 3. If the measured electric potential difference across the membrane is of same sign to the electric potential calculated from the Nernst equation for a particular ion, but numerically more than the latter, then the electrical force is larger than the concentration force. So, net movement of that ion occurs in the direction of electrical force. 4. If the measured electric potential difference across the membrane is of opposite sign to that calculated from the Nernst equation for a particular ion, then both the electrical potential and concentration forces are aligned in the same direction. Such an ion will move under the combined force of both the electric and chemical potentials. Thank you for watching this till the end. In the next video we shall look into 1. How the Nernst potential and Gibbs-Donin equilibrium together come to decide the resting membrane potential. 2. How the voltage changes that occur during an action potential are also decided in part by the Nernst potential. 3. The genesis of the chord conductance equation or the Goldman-Hodgkin-Katz equation.